Hello everyone. This video will show about the radius of drawing punch and die. Now, let us go into engineering campus of University Science Malaysia. First of all, I will introduce about drawing process. Drawing is a metalworking process which uses tensile force to stretch metal or glass. As the metal is drawn, it stretches thinner into a desired shape and thickness. Drawing is classified into two types: sheet metal drawing and wire, bar, and tube drawing. This video will focus on dip drawing process. Dip drawing is a common process in industry for manufacturing products from sheet metal. Very complex products can be achieved using dip drawing, such as automotive parts, cans, sinks, and housing. Here an example shows the drawing of a circular cup. The process is described in the following steps. Firstly, the circular blank is inserted between die and blank holder. Then, the punch moves downwards and the diameter of the blank decreases with the blank being drawn into the die cavity. Finally, the flange of the blank forms the perpendicular wall of the cup and the center part of the blank forms the bottom of the cup. There are few important dimensions of the blank, die, punch and blank holder which will affect the dip drawing process. However, we will focus only on the die entry radius and the punch radius. First factor, die entry radius. The die entry radius is the radius connecting the cavity wall to the die face. It is one of the most critical radius to size and finish properly. The die entry creates a restrictive force by causing the metal to bend and unbend during the drawing process. If the die entry radius is too large, the metal is in compression. There is little restrictive force to keep the metal from flowing in, and it might wrinkle in the radial area of the part. This wrinkling can cause cosmetic problems as well as splitting when the metal is forced to unwrinkle in the wall of the drawn cells. This unwrinkling creates a resistance to flow that results in more stretch. Second factor, punch radius. The punch radius at the top of the punch is also critical. The size of the punch radius often determines how much stress will occur in the product and how much metal will be forced to be pulled from the blank holder. A very large radius with a high blank holder force or draw bit will force a great deal of stress to be obtained in the product. A large punch radius with a low blank holder force will result in a combination of flow and stress. A small punch radius will force the metal to be pulled from the blank holder and very little stress will occur in the product area. A small radius usually is acceptable only when the limiting draw ratio is not being defined. A medium-sized punch radius combined with an acceptable limiting draw ratio is optimum for stress distribution in the radial area. That's all. Thank you for watching. Bye!